Howdy, my name is Zachary Lawson from Dr. Moreno's Biomedical Environments Lab. This is my research on mechanical push-out evaluation of bioactive self-fitting shape memory polymer scaffolds to treat cranial bone defects. Confined cranial defects can be caused by tumor, infection, trauma, or surgical burr holes from craniotomies. The leading treatment option is to use autologous bone grafts. However, this autograft approach is limited by difficulty in harvesting and shaping the autograft to tightly fix into the irregular geometry of the cranial defect. Other treatments, such as PEEK and PMMA bone cements, are less common due to high exothermic curing temperatures and inferior osteointegration. Overall, cranial defect repair is associated with a 10 to 40% complication rate. Tissue engineering approaches have produced promising alternatives in terms of matching defect geometry and promoting bone healing. To this end, a multiple shape memory polymer scaffold has been developed with highly interconnected pores coated with a bioactive polydopamine and seeded with patient-derived MSCs. These SMPs can be self-fitted into irregular confined cranial bone defects. This study focuses on evaluating the mechanical performance of the SMP graft in comparison with the standard autograft treatments using push-out testing on rat cranial models. 48 Sprague Dawley rats were induced with bilateral cranial defects of a nominal 5 mm diameter, then subdivided into 8 treatment groups and terminated after a time point of 4 weeks. The first group received the control autograft, while the remaining groups received an SMP scaffold composed either of the PLLA-based scaffold A or PDMS scaffold B. The scaffolds were coated with polydopamine and or seeded with cells, with the low treatment receiving 35,000 cells and high treatment receiving 4 million cells. Despite the ubiquity of the push-out test for cranial defect evaluation, there is in fact no standardized approach for ensuring rod alignment, sample security, and positioning, so we developed our own novel method to address these concerns. A custom 3D printed clamp with 6.5 mm through-hole was used to clamp to the X-size skulls from the top and the bottom, centering the through-hole on the defect. A targeted notch pattern was printed on the top of the clamp, centered on the through-hole, and a mating alignment cylinder attached to the push-out rod. With the specimen secured in place, the clamp was then attached to a Newport linear stage and adjusted under the crosshead of a mechanical testing machine. Sample position was verified by mating the position aligner to the target notch on the top clamp. The push-out rod was displaced at 1/2 mm per minute until failure. Load at failure and stiffness were compared using ANOVA with Tukey post hoc to evaluate significance. As you can see, at the 4-week time point, the SMP treatment shows a favorable mechanical performance compared to the autologous bone graft treatment, with both of the non-cell seeded scaffold A treatments showing significantly higher loads. These mechanical tests indicate better mechanical integrity and integration of the SMP compared to the autologous bone graft treatment. Future work includes repeating these tests at a 12-week time point and modifying the clamp to allow for increased visibility, particularly of the failure mode. I would like to thank and acknowledge the work of my lab in the Biomedical Environments Lab and the members of the Grunland Research Group as well. Thank you for your time.